So as promised, I'm going to do some more applications using quadratic equations. But what I'm going to do is going to be a little bit different from what Steve just took you through. We're going to start by working with formulas, and then we're going to do some problems where we'll be modeling with quadratic equations. So let's start with some formulas. Here's an example. We're given the formula a squared plus b squared equals c squared, and we're asked to solve it for b. Well, this formula probably looks familiar to us. So what we're being asked to do here is to find the lengths of one of the legs of a right triangle in terms of the other leg and the hypotenuse. So let's solve this formula for b. So what I need to do here is isolate b squared. So I'm going to start with the Pythagorean theorem, or at least that's what I'm supposing this formula is. I'm going to subtract a squared from both sides, and now I can use the square root property and write that b equals plus or minus the square root of c squared minus a squared. Now I've done what it was asked. I have solved this formula for b. And there are actually two possible formulas given by this expression. B is the positive square root of c squared minus a squared, and b is the negative square root of c squared minus a squared. But if b is indeed the leg of a right triangle, then we're only going to be interested in the positive square root here. So if b is the length of one leg of a right triangle, then we just want b equals the square root of c squared minus a squared. Here's another example. K equals 1/2 mv squared, and we're asked to solve for v. We're asked to solve for the factor that's squared because we're solving quadratic equations. Now I like to know where my formulas are coming from. This is a formula from physics. K is the kinetic energy of a body of mass m traveling at a speed v. But we're just asked to work with this mathematically and solve for v. Now here I want to isolate v squared. I'm going to start by clearing that fraction, multiplying both sides of my formula by 2. Now to isolate v squared, I can divide both sides of the formula by m. So now I have v squared equals 2k over m. Using the square root principle, I have v equals plus or minus the square root of 2k over m. Now since v is a speed, I'm only going to be interested in the positive square root. So my formula that will give me the speed in terms of a body's kinetic energy and mass is this formula. Now you might be asking, well, why isn't n going to rationalize the denominator? Well, typically we do not do this when the denominator under the radical is a variable. And also, if I was using this formula, I would probably just plug in numbers for k and m and calculate the resultant speed. One last example with a formula. Here we have the formula y equals negative 5t squared plus 10t, and we're asked to solve for t. Now this formula might be giving us the height of a bottle rocket in meters shot from the ground with an initial velocity of 10 meters per second, and this will be the height after t seconds. Now I'm saying this is roughly the height because I rounded off this number here, the negative 5, to make the numbers work out a little bit nicer here. This actual number is more like negative 4.9. So now we're asked to solve for t. Now this is a little bit more problematic because in this situation I have both a term with t squared and another term with t. I can't just isolate t squared and use the square root property. So what I'm going to do here is treat this like a quadratic equation. It is a quadratic equation. So I have y equals negative 5t squared plus 10t. When I solve a quadratic equation, either using the quadratic formula or by factoring, I need to have 0 on one side of the equation. So I'm going to add 5t squared to both sides, subtract 10t from both sides, and now I have a quadratic equation in t. It looks kind of funny because of that y there, but this is at squared plus bt plus c equals 0, and in this case, a equals 5, b equals -10, and c is a variable y. Let's solve for t using the quadratic formula. So t equals the opposite of b, so that's going to be 10, plus or minus the square root of b squared minus 4ac all over 2a. Simplifying this a little bit, I get t equals 10 plus or minus the square root of 100 minus 20y all over 10. Now I have a formula for t. So this original formula was giving us the height of a bottle rocket in terms of time. This new formula will give us the time in terms of the height of the bottle rocket. So if I want to know at what time the rocket hit a particular height, I would just plug that height into this formula and evaluate t. So let's discuss the practical significance of the discriminant of the new formula. Here's the formula we just came up with for t in terms of y. The discriminant is the expression under the radical. So what I'm going to do is create a table to look at the 3 possible cases. So the first case is the case where the expression under the radical is positive. In this situation, we're going to have 2 solutions to the quadratic equation. There's going to be 2 values of t. Now, to write that conclusion, the practical significance would be, in this case, there will be 2 times the bottle rocket is at height y. Now what's the situation here? Well, the situation here, if I solve this inequality for y, I have 100 is greater than 20y, so y would have to be less than 5 meters. So as long as we're looking for the height of a bottle rocket below 5 meters, we're going to get 2 times that the rocket hits that height. Now, one of the things about this particular bottle rocket is it's kind of a dud too, because it's not going too high, and we'll see that in the next situation. If the expression under the radical, the discriminant, is 0, we're only going to get 1 time the bottle rocket reaches its height. So in this case, when y equals 5, that's a solution to that equation. In this case, there will be only 1 time the bottle rocket is at height y, 5 meters. So there's going to be just 1 time that the bottle rocket's at 5 meters. What about this situation? Well, solving this inequality, this is where y is greater than 5. Now what happens here? Now the discriminant is negative, there are going to be no real number solutions to the quadratic equation. And what this means is that the bottle rocket will never hit that height. So in this case, there will be no times the bottle rocket is at height y. So here's a situation where the bottle rocket is just not going to hit a height anything greater than 5 meters. So now let's do some modeling with quadratic equations. Here's our first problem. Manny volunteers to schedule baseball games for a summer league that plays in Portland parks. In this league, each team plays every other team once before the playoffs. The number of games Manny schedules depends on how many teams are in the league. The question is, how many teams are there in the league if 190 games are played? What makes this problem different than some of the problems that Steve worked with you is that we don't have a formula here to work with. We're going to have to come up with it ourselves. So we're going to kind of think about this a little bit. We're going to start with kind of a basic question. How many games must be scheduled if there is only one team in the league? Now you might think this is a bizarre question. It's not very practical. But it's a mathematical question and we want to be able to consider all the possibilities. Well, if there's only one team, it's not going to be playing any other team and there will be no games played. So, if there is only one team, no games will be played. So now what we're going to do is we're going to complete a table, and we want to establish a pattern between the number of teams in the league and the number of games played. So here's our table. We already figured out that when there's one team in the league, no games are going to be played. What if there are two teams in the league? Well, I'm going to draw a picture here because that will help us visualize this situation. There are two teams in the league. They're going to play one game. That's pretty easy. What if there are three teams in the league? Well, we're going to add a new team, and that new team has to play each of the prior teams that were in the league. Two more games are going to be played. Altogether, there are 3 games, but we're adding 2 more games to the game that was played with only 2 teams. What if there are 4 teams? Well, adding this new team's going to have to play each of the other 3 teams that were already there. So we need to play 1, 2, 3 more games. So we have 1 plus 2 plus 3 games, or 6 games altogether. Let's do this one more time. I'm going to add a 15. This 15 has to play the 4 teams that were already in the league. So we're going to add 1, 2, 3, 4 more games. So we're going to take the 6 games that were already played and add 4 more. So now we kind of see a pattern here. What we're doing is we're adding up natural numbers. Now, we could work with this a little bit and try to come up with a formula, but we might remember that in a previous lesson, we actually looked at a formula for the sum of the first n natural numbers. And here's the formula. Now here, something's a little bit different though, because now, when we have 2 teams, 1 game is played. When we have 3 teams, we have 1 plus 2, so we're adding up the first 2 natural numbers. When we have 4 teams, we're adding up the first 3 natural numbers. So if n is the number of teams in the league, then we're adding up the first n minus 1 natural numbers. That sounds kind of complicated. But what I'm doing is I'm replacing n with n minus 1, and when I do that, I get a formula that's very similar to the formula I had for the sum of the first n natural numbers. Now let's make sure this formula works. Let's plug in n equals 4, for example. If n equals 4, that means we have 4 teams, then the number of games played is 1/2 times, well, let me write my formula, n minus 1 times n. That would equal 1/2 times 4 minus 1 times 4, which is 1/2 of 12, which is 6. And notice, I had 6 games. So my formula is working. Now we have to answer the question. How many teams are in the league if 190 games are played? Well, we have our formula for the number of games played with n teams in the league. So I want to solve the equation 1/2 n minus 1 times n equals 190. This is going to be a quadratic equation. So distributing n through n minus 1, I have 1/2 n squared minus n equals 190. So multiplying both sides of the equation by 2, I'm left with n squared minus n equals 380. To solve this either using the quadratic formula or by factoring, I need to subtract 380 from both sides. Now, when I was simplifying this equation, I noticed that 2 times 190 is 380. I also noticed that 20 times 19 is 380. So I'm looking for integer factors of negative 380 that add to negative 1. Well, negative 20 and positive 19 are going to work. So I have n minus 20 times n plus 19 equals 0. If you don't see that factorization, you could use the quadratic formula and you'd still get the solutions. So I have two possible solutions, n equals 20 or n equals negative 19. But in this case, n represents the number of teams in the league, so I can't possibly have negative 19 teams playing in the league. Well, what if I have 20? Let's check. If there are 20 teams in the league, then I'm going to count the number of games played. Using my formula, I have 1/2 n minus 1 times n. That will equal 1/2 times 19 times 20. 1/2 of 20 is 10. 10 times 19 is 190. And this is how many games are played. So in the process of doing a check, I've got a pretty good conclusion, and I'm going to leave it at that. One last problem. PCC's theater department sold tickets to the opening night performance of Proof for $10, and 150 people attended. The next night, ticket prices were reduced by 25 cents, and 10 more people attended. So the price went down, more people bought tickets. Assuming that further price reductions of 25 cents will result in 10 additional tickets sold, after how many price reductions will the department's revenue be $1,500? So what we're going to do is we're going to make another table to establish a pattern between the number of price reductions and the department's revenue. So here's my table. Now the first thing I'm going to look at is, what if there are no price reductions made? Well, how am I going to calculate the revenue? Well, revenue is going to be the unit price, the price of a ticket, times the number of units sold, in this case the number of tickets. We were told that on opening night, the tickets were $10 per ticket and that 150 tickets were sold. This gives us a revenue of $1,500. Now the problem was asking us, when will the department's revenue be $1,500? Well, they were the first night. But now we want to know, are they going to be $1,500 again? Let's see what happens when they make a price reduction. When they make the first price reduction, we're going to subtract 25 cents from the price of a ticket. And now 10 more people show up. So we're going to sell 150 plus 10 tickets. So we have $9.75 per ticket times 160 tickets. Let's calculate that to see what the revenue is. So $9.75 per ticket times 160 tickets. The revenue has now gone up. So think about this a little bit. The price of the ticket's going to keep going down. Would we expect the revenue to keep going up? Well, probably not. Eventually the tickets will even be given away for free, that the theater department won't be bringing in any money from the sale of tickets. So I'm going to assume that the revenues are going to go up and come down. So let's continue with our table. So I'm leaving my expressions kind of in pure, raw form so that we can see a pattern. After two price reductions, we start with our $10 per ticket, and we're going to subtract 25 cents twice. How many people attend? Well, originally 150 people attend, and for each price reduction, now there are two, 10 more people come. How about if there are three reductions? Now we're going to subtract 25 cents from the original $10 three times, so we're subtracting 75 cents. And now 30 more people are coming. So now let's suppose that X is the number of price reductions. Can we see a pattern? Well, what's changing? What's changing is what we're multiplying 25 cents by. First we multiply it by 1, then by 2, then by 3. This is the number of price reductions, which we're calling X. Let's look at the number of tickets sold. We take 150, first we add 1 10, then we add 2 10s, then we add 3 10s. So 3 is the number of price reductions. So it seems to me that the pattern should be 10 minus 0.25 times the number of price reductions, that's the cost per ticket, times the number of tickets sold, which would be 150 plus 10x. Here's an expression for the revenue. So now the question was, after how many price reductions will the department revenue be $1,500? So here's the expression we just came up with. Let's write an equation. We want to solve the equation 10 minus 0.25x times 150 plus 10x equals $1,500. Now to solve this equation, I need to expand the left-hand side. So using FOIL, the product of the first terms is 1,500. Product of the outside terms is plus 100x. Product of the inside terms, let's see, I need to figure out 1/4 of 150. That's going to be 37.5. And then finally, the product of the last terms is minus 2.5x squared. This equals 1,500. I have a constant term of 1,500 on both sides. So when I simplify, I end up with 62.5x minus 2.5x squared equals 0. This is actually a pretty easy quadratic equation to solve because I notice I have a common factor of x in each of the terms on the left. So factoring that out, I leave behind 62.5 minus 2.5x. Using the zero product principle, I have x equals 0 or 62.5 minus 2.5x equals 0. So x equals 0, this corresponds to no price reduction, and we already figured out that on opening night, the theater department's revenues were $1,500. This is the other situation that we're interested in. So solving that equation, I have 2.5x equals 62.5. So x equals 62.5 over 2.5. Let's calculate it. 62.5 divided by 2.5, that's 25. So we have a second possible solution. After 25 price reductions, we're expecting the theater company's revenue to be $1,500. Well, let's check. So, after 25 price reductions, the price of the ticket is going to be $10 minus 0.25 times 25. We have 25 price reductions. So that's 10 minus 6.25, so this is going to be $3.75. How many tickets are sold? Well, we have 25 price reductions, so we have 150 plus 25 increases of 10 tickets sold. This is going to be 400 tickets sold. So let's check the revenue. We need to multiply 400 by 3.75. So we have 400 tickets sold at $3.75 per ticket, and indeed the revenue is $1,500. So our answer checks. So to state a conclusion, on opening night, and after 25 price reductions, the department's revenue will be $1,500. So this ends my part of the lesson. Candace is now going to come and talk to us about graphing.
In this part of the lesson, I'm going to talk about graphing linear and quadratic equations. I'm going to start by reviewing the graphs of linear equations in two variables. We talked about linear equations in quite a bit of detail in Math 60, and we graphed all kinds of lines. At the beginning of Math 65, we also looked at graphs of linear equations when we were studying systems of linear equations. I'm going to give a brief introduction to the graphs of quadratic equations in two variables, which we'll go into in a lot more detail in the next lesson. I'm going to review horizontal intercepts for lines, and then I'm going to talk about the horizontal intercepts for quadratic equations in two variables. So let's review the graphs of linear equations in two variables. Remember that a linear equation with two variables, x and y, can be written in the form ax plus by equals c, with the condition that a and b cannot both equal 0. Also remember the solution set to a linear equation with two variables is a set of ordered pairs that graphs to a line. So let's fill in the table and plot x plus y equals 8. By looking at the graph of a linear equation, hopefully we'll get grounded back into the fact that when we're working with an equation in two variables, we get ordered pairs, and in the case of a linear equation, those ordered pairs graph to a line. So in table 1, when x is 0, what does y have to be? Well, looking at our equation, we know that x plus y equals 8. Since 0 plus 8 equals 8, y must be 8. Likewise, if y is 0, then x must be 8. What about if x is 4? Well, thinking of our equation again, x plus y equals 8, so 4 plus y equals 8, so y must be 4. What about if y is 2? Well, since x plus y equals 8, that means x plus 2 equals 8, so x must be 6. Likewise, if x is 2, then y must be 6. 2 plus 6 again is 8. So let's plot the ordered pairs this table leads us to. First, we have the ordered pair 0, 8. This is going to be our vertical intercept. Then we have the ordered pair 8, 0. This is going to be our horizontal intercept. We have the ordered pair 4, 4. We have the ordered pair 6, 2. And we have the ordered pair 2, 6. Now I'm going to get out a straight edge and graph the line that goes through these points. Looking at this line, it looks like 1, 7 might also be a solution to this equation. Let's see if it really is. If x is 1 and y is 7, 1 plus 7 indeed does equal 8. So the ordered pair 1, 7 is a solution to this equation. We talked about three forms of linear equations: standard form that we just mentioned, slope-intercept form, and point-slope form. A lot of times when we're graphing, we use slope-intercept form, because in slope-intercept form, we can easily read the coefficient of x, m, is the slope of the line. And looking at our constant b, we know that 0b is the vertical intercept of the line. Let's graph this line given in slope-intercept form. Y equals 3/2 x minus 6. Well, since the constant here is negative 6, I know that the vertical intercept is going to be 0, negative 6. Let's plot that. The coefficient of x, 3/2, tells me the slope. So the slope is 3/2. Thinking about rise over run, I have a rise of 3 and a run of 2. So starting at my vertical intercept, 0, -6, I rise 3 and run 2. I rise 3 and run 2. Now getting out my straight edge, I'm going to plot the line that goes through these points. Just as a quick check, let's make sure that one of these points that I got using the slope actually does satisfy this equation. So it looks like here I have the point 6, 3. Well, let's see if we let x be 6 if y really is 3. Well, if x is 6, then we're multiplying 3/2 times 6. 2 goes into 6 3 times, and then 3 times 3 is 9. 9 minus 6 gives me a y value of 3. That's what the y value was supposed to be, so this point does check. Let's do one more linear graph. Let's graph d equals -2t plus 7. Again, this is in slope-intercept form. My constant 7 tells me that the vertical intercept is 0, 7. Let's plot that point. The coefficient of t, in this case -2, tells me the slope. I can think of -2 in fractional form as -2 over 1. Thinking about rise over run, that gives me a rise of -2 and a run of 1. So starting at my vertical intercept 0, 7, I would go down 2 to the right 1. Down 2, right 1. And then pulling out my straight edge again, I'll sketch the line that goes through these points. One thing I notice about this line is that it's always decreasing. This makes sense. The line has a constant slope of -2, so our line is decreasing at a constant rate. Now I want to do a brief introduction to the graphs of quadratic equations in two variables. Let's complete the table for the quadratic equation y equals x squared minus 4. So I have x values of -3, -2, -1, 0, 1, 2, and 3. Well, let's start with if x equals -3. Then y is going to be the square of -3 minus 4. That's 9 minus 4, which is 5. What about if x is -2? Well, if x is -2, then y is going to be the square of -2 minus 4. The square of -2 is 4, and 4 minus 4 is 0. Let's try to do some of these in our head. What if x is -1? Well, then y is going to be the square of -1, that's +1, and 1 minus 4 is -3. So when x is -1, y is -3. What about if x is 0? Then we have y equals 0 squared minus 4. That's 0 minus 4, which is -4. What about if x is 1? Then y is 1 squared, that's 1, minus 4. 1 minus 4 is -3. What if x is 2? Then y is 2 squared minus 4, that's 4 minus 4, which is 0. And finally, what if x is 3? Then y is 3 squared minus 4, that's 9 minus 4, which is 5. Now this is definitely not the table for a linear equation in two variables. If we look at our x values, we see that all of the x values increase by 1 each time, -3, -2, -1, and so on. But what about the y values? Well, the y values start at 5, decrease to -4, and then increase to 5. So they're not always increasing, they're not always decreasing. They're also not changing by constant amounts. Even though x is increasing by 1 each time, y decreases by 5, decreases by 3, decreases by 1, then increases by 1, increases by 3, and increases by 5. Let's graph the 7 points that we just found. Now, what a lot of students will do when they first start working with quadratic equations is think about linear equations. When we're graphing a linear equation, we get out our straight edge. So they might take out a straight edge and use straight line segments to connect the points. If we do that, our graph looks something like this. However, we can't do this. What this is implying is that the slope between the points that we happen to plot is constant. We already talked about the fact that it's not. Y is changing at different rates while x is increasing by 1 each time. What we actually get here is a curve. So notice the difference between the graph we would get, which we're showing right now, by connecting the points with line segments and actually sketching in a curve between the points. This curve is called a parabola. The solution set to a quadratic equation with two variables is a set of ordered pairs that graphs to a parabola. We're going to talk about the graphs of parabolas more in lesson 16. Right now I want to go back and review horizontal intercepts. So I'm going to start by talking about horizontal intercepts for linear equations. Remember that for a linear equation of the form ax plus by equals c, the x-intercept is the solution to the equation of the form x sub 0, 0. So let's find the horizontal intercept of the line with equation y equals 3x minus 4. Well, we want our y value to be 0. So if y equals 0, then we have 0 equals 3x minus 4. Solving for x, I can add 4 to both sides of the equation. So 4 equals 3x. And dividing both sides of the equation by 3, we get 4/3 equals x. So this tells us that the horizontal intercept is 4/3, 0. Well, what about quadratic equations? For a quadratic equation of the form y equals ax squared plus bx plus c, the x-intercepts are also the solutions to the equation of the form x sub 0, 0. So if we want to find the horizontal intercepts of the parabola with the equation y equals x squared minus 9x plus 20, we again need to let y equal 0. So if y equals 0, then we have 0 equals x squared minus 9x plus 20. Now it looks like I can factor that expression on the right-hand side of the equals sign, because negative 4 times negative 5 gives me that constant of 20 at the end, and negative 4 plus negative 5 gives me the negative 9 for the coefficient of x. Now the zero product property tells me that x either has to equal 4 or x has to equal 5. So this parabola has two horizontal intercepts. The horizontal intercepts are 4, 0 and 5, 0. I want to verify this on a graph. So I've had the computer create a graph for us. We're going to talk more in lesson 16 about how to create these graphs on our own. For now, we're just going to use this for verification purposes. So here's a graph of y equals x squared minus 9x plus 20. Let's look at our horizontal intercepts. It looks like we have a horizontal intercept at 4, 0 and another horizontal intercept at 5, 0. That's exactly what we just found. So the graph verifies our results. Now let's find the horizontal intercepts of the parabola with equation h equals t squared minus 9t. So this time we're looking at ordered pairs of the form t, h. So if we're looking for the horizontal intercepts, we're looking for the t-intercepts. We need to let h equal 0. So if h equals 0, then we have 0 equals t squared minus 9t. Now it's easy to factor the right-hand side of this equation. I have a common factor of t in both of the terms. So if I pull out that common factor of t, my remaining factor is t minus 9. And the zero product property tells me that either t has to equal 0 or t has to equal 9. So this parabola also has two horizontal intercepts. The horizontal intercepts are 0, 0, the origin, and 9, 0. Again, let's look at a graph to see if this really is the case. Here's a graph of h equals t squared minus 9t. Where are the horizontal intercepts? As we expected, there's a horizontal intercept at the origin. There's another horizontal intercept over here at 9, 0. So the graph really does verify what we found. Now let's find the horizontal intercepts of the parabola with equation d equals t squared minus 6t plus 9. This time we need to let d equal 0. So if d equals 0, then we have 0 equals t squared minus 6t plus 9. Now I think I can factor that right-hand side of the equation. Negative 3 times negative 3 will give me the constant positive 9 at the end, and negative 3 plus negative 3 will give me the coefficient of t, which is negative 6. So now the zero product property tells me that either t has to equal 3 or, well, t has to equal 3. It looks like this parabola only has one horizontal intercept. So that horizontal intercept is 3, 0. Let's look at a graph. Here's a graph of d equals t squared minus 6t plus 9. It does look like there's only one horizontal intercept. Where is it? Well, it looks like at the point 3, 0. That verifies what we just found. Now let's find the horizontal intercepts of the parabola with equation y equals 3x squared plus 5x minus 4. This time we need to let y equal 0. So if y equals 0, then we have 0 equals 3x squared plus 5x minus 4. Now I'm not thinking real quickly of a way to factor that right-hand side of the equation, so I think I'm going to go ahead and apply the quadratic formula. So the quadratic formula tells me that x has to equal the opposite of b, so that's negative 5, plus or minus the square root of b squared, so that's 5 squared, minus 4 times a, which is 3, times c, which is negative 4, all over 2 times a, that's 2 times 3. Simplifying, I have negative 5 plus or minus the square root of 25 plus 48 all over 6. So this is negative 5 plus or minus the square root of 73 all over 6. So it looks like I'm going to have two horizontal intercepts. If I want to verify this on the graph, though, I need an idea of where these numbers lie. So I'm going to get a decimal approximation for these two x values using the calculator. So first I have negative 5 plus the square root of 73 divided by 6. This is about 0.59. What about negative 5 minus the square root of 73 divided by 6? This is about negative 2.26. So it looks like there are two horizontal intercepts, and we've approximated the x values here. So I'll say about 0.590 and negative 2.260. Let's look at a graph and see if we can verify these results. So here's a graph of y equals 3x squared plus 5x minus 4. Let's look at our horizontal intercepts. We said one was about negative 2.260. This seems reasonable. And we said the other was about 0.590. This also seems reasonable. So our graph seems to verify our results. Now let's find the horizontal intercepts of the parabola with equation y equals 2x squared plus 3x plus 4. So again, I need to let y equal 0. So if y equals 0, then we have 0 equals 2x squared plus 3x plus 4. Thinking about this one, I know I'm not going to be able to factor the right-hand side. I'm looking for two integers that multiply to give me 2 times 4, which is 8, and add to give me 3. There aren't any two integers that multiply to give me 8, but add to give me 3. So I have to use the quadratic formula here. So the quadratic formula tells me that x would have to equal the opposite of b, that's negative 3, plus or minus the square root of b squared, that's 3 squared, minus 4 times a, which is 2, times c, which is 4, all over 2a, which is 2 times 2. Simplifying this, I have negative 3 plus or minus the square root of 9 minus 32, all over 4. So this is negative 3 plus or minus the square root of negative 23, all over 4. Now hopefully you're looking at this and worrying about that negative under the radical. The discriminant is negative here. That should be telling me something. And in fact it does. When a quadratic equation is solved by the quadratic formula and the discriminant is negative, then we know the quadratic equation has no real number solutions. So the equation 0 equals 2x squared plus 3x plus 4 has no real number solutions. This tells us that the parabola y equals 2x squared plus 3x plus 4 has no horizontal intercepts. Now I really think I want to verify this one with a graph. So here's a graph of y equals 2x squared plus 3x plus 4. We just decided that this graph would have no horizontal intercepts. Well, look at our parabola here. The parabola is always above the x-axis. My lowest point here is above the x-axis. There are no horizontal intercepts. So this verifies our results. This is the end of our lesson on quadratic applications and an introduction to graphing quadratics. In the next lesson, we're going to spend quite a bit of time graphing quadratic equations in two variables.
1, 2.